Energy conservation is the idea that energy cannot be created or destroyed. It can change forms from one form to another, but it can't actually, you can't get more, you can't take any away from the total sum of the universe. This also applies to smaller universes, any isolated system. Any system that's not being acted upon by outside forces or outside effects it will obey this conservation law. Disclaimer, it's not actually true. Energy can be created from mass and can also be converted into mass. The correct law is the conservation of mass energy. That is always conserved. But in general, in our everyday interactions, that's kind of extreme cases. In our everyday interactions, energy really is conserved. So, again, conservation of energy, energy cannot be created or destroyed, but can and will change forms often. So, to approach problems, to solve problems using conservation of energy, there's 3 steps. The first step is to identify the type and amount of energy that you start with. And this could be any kind of energy. Kinetic, potential, elastic, we don't know. You have to look at the problem. And we call this E sub I, for E initial. If you want to call it E naught, that's fine too. Totally your call. That's step 1. Step 2 is the same exact thing, except it's the amount of energy that is ended with. There should be a with here. Ended with. And this is our final energy, EF. Okay? So you start with some amount of energy, you end with some amount of energy. The key is identifying what kind do you start with, what kind do you end with. It probably changes forms. Otherwise, it's not a very interesting problem. And step 3 is to set EI equal to EF, and then solve for whatever quantity you have that you desire. Three steps. Using these 3 steps, you'll be able to solve essentially any energy problem that comes your way. Unlike with forces, where some of the difficulty in forces came from the mathematics and making these substitutions and canceling things out and plugging them back in and solving multiple equations at the same time, this is going to be mathematically simpler. You're going to have one equation, and you're going to solve for one thing, and that's it. The difficult part here is going to be gaining an intuition and figuring out what kind of energy you start with and what kind of energy you finish with. So, once you get that and you set them equal, you're done, basically. Then it's just algebra. So, let's go ahead and do an example. Let's say I have a ball of mass m is dropped from a height of h. And I want to know, what is the velocity of the ball the moment before it hits the ground? Right before it hits the ground. So we're going to do this with conservation of energy. You know how to do this with kinematics if you've done kinematics. But energy is going to be a nicer, cleaner, easier way to go about doing this. So, step 1 is to identify what energy we have at the beginning of the problem and how much of it. So the energy at the beginning, it's being dropped. So it has no velocity, there are no springs anywhere, so that just leaves potential energy. We're near the Earth, so we can use U, or we can use that the initial energy is equal to U, right, which is mgh. That's going to be the energy we start with. Step 2 is how much energy do you finish with. So as you're moving down, you get really close to the ground, now it is moving, right? But now the height above the ground is essentially 0. So we don't have any potential energy anymore, we do have kinetic energy. So my final energy is kinetic, which is 1/2 mv squared. Step 3, I'm going to set these two things equal to each other. EI equals EF. And then I can go ahead and solve for my desired quantity, which is speed. So I have mgh is equal to 1 half mv squared. The m's cancel out. You're left with v squared is equal to 2gh, where I multiplied both sides by 2. So then v is equal to the square root of 2gh. That's the velocity of the ball right before it hits the ground. So here, energy stays the same, just converts from potential to kinetic. That's the change that's happening. You really only see the effects of energy when it's changing form. So, let's go ahead and do one more. Suppose I have a spring and I put a ball of mass m on the end. And my spring has a spring constant of k. And let's say that I take this spring and I compress it. And now I've compressed it a distance of x. So I compress the spring, and then I release it. So the spring decompresses and shoots forward, and the ball launches forward. Right? And it launches forward with some speed v. And in this problem, I want to find what speed is the ball launched with. So to do that, same three-step process. Step 1, what does the energy start with? Well, you start here. The ball's not moving, so no kinetic. You don't really have gravity, so you're not going to use gravitational potential, but you have a spring. So elastic potential energy. So your initial energy is equal to 1 half kx squared. Step 2, your final energy. So here, the ball is shooting forward, right? So it's moving, so it has a speed, so we're going to use kinetic energy, so 1 half mv squared. No potential or anything like that. You can have more than one type of energy at any point, and if you have multiple kinds in one step, just add them together. Step 3, I'll do over here. We're going to set EI equal to EF, and that gives us 1 half kx squared is equal to 1 half mv squared. And then from there, our 1 halves cancel. And solving for v squared, we get v squared is equal to kx squared divided by m. So then v is equal to the square root of kx squared over m. And we can simplify this by pulling out the x squared. So we get v is equal to x times the square root of k over m. And that's the velocity that the ball is launched with. So, that is energy conservation in a nutshell. Problems will get harder. These are very straightforward, very simple problems with one kind of energy, no kind of weird physical scenarios going on here. Very straightforward. Nonetheless, this three-step process, if used, every energy problem will give you, is the approach that you want to take and will give you the correct solution.